Hello and welcome to the week 4 pre-lab 32E. So this is going to cover 3.7, which you went over briefly in the lecture, and 3.10, as well as 4.1 and 4.5. But with chapter 4, we're going to barely scratch the surface. We're just telling you only what you need to be able to understand the lab this time. So, for review, an ionic bond is made through an exchange of electrons with nonmetals taking electrons, and they're taking them from metals, forming anions and cations, respectively, and those are held together by electrostatic forces. And that just means that the opposite charges very strongly attract each other to form these compounds. So let's talk about the crystalline structure. So when ionic compounds form crystals, every single atom is ionically bonded to all adjacent atoms. So let's draw a picture of that. So let's do NaCl, sodium chloride. So if I've got to make that bigger. Okay, each one of these is an ionic bond. Now I've got the trick. Write the letters before. You want to try and make this a 3D picture? Okay. No, that's enough. Nope, it doesn't want to let me erase it. There we go. Okay, we don't have to have great art skills. Okay, so let's look at covalent bonds, just the basics of covalent bonds. Oh, trying to scroll up and it's just wanting to mark. There we go. Okay, that was weird. Okay, so covalent bonds are made by sharing of electrons. All right, there's no charges involved. And that sharing of electrons occurs only between nonmetals. Okay, and so one unit of a covalent compound is called a molecule. Okay, so let's look at elemental chlorine, Cl2. So I've got two Cls, okay, and they're each missing one electron to form an octet. So they're going to share these two electrons and give each atom the illusion of an octet. Each chlorine atom thinks that the two electrons in between are theirs. So each one thinks it has an octet. So one thing we'll do later is we'll represent these bonded electrons with a line. Okay, a line of sharing electrons. So let's look at the difference between two types of covalent bonds. And those are going to be polar and nonpolar covalent bonds. And, and again, we're going to go into much greater detail next week. So similar atoms. Similar atoms will share electrons equally. And that forms what we call a nonpolar bond. Okay, it's totally neutral. No semblance of a charge whatsoever. Not full charges, not partial charges. So if I have a CH bond, that's equal. C and H are similar enough. If I have that Cl bond, these are the same atom, so it's definitely equal. Okay, and if you have, say, a chain of carbons, like we see in organic molecules, I should have drawn this shorter. Now I have a whole bunch of hydrogens to draw in. But this would be a nonpolar molecule because none of these bonds are polar. Okay, so if you have other more different atoms, those will share electrons unequally, forming a polar bond. So it's still technically neutral, but it has very slight charges on either end. Okay, so let's look at some examples. So that is a polar bond. And so this side is slightly negative, and this side is slightly positive. Okay? It's kind of like an ion, but it's not, because they're only slight charges. So let's look at a C. This is called a double bond. That's going to be slightly positive, and that's going to be slightly negative. And let's look at a water molecule. It has an overall polarity. Since these hydrogen atoms are on the same side, that side is slightly negative, and this side is slightly positive. It's a polar molecule. So what is the crystalline structure of um, a molecular, or also called a covalent compound. So molecules in the solid phase are held together by intermolecular forces, which are much weaker than bonds. So sugar is an example of a covalent compound. Um, don't worry about how we're drawing it. Just go with me here. Okay, and so they're held together with these intermolecular forces, much weaker than a bond. You'll see drawings like that a lot more in organic chemistry, so this is just a quick introduction to that. So let's look at some properties of ionic compounds. So the fact that the crystalline structure of ionic compounds is held together through bonds formed by electrostatic forces. Okay, that's responsible for its physical and chemical properties. So let's look at solubility. Water is a polar solvent. A solvent is just the major portion of a mixture. So if we put a little bit of salt in water, then water is the solvent. Okay. So water is a polar molecule, and the slight charges can disrupt ionic bonds. They can disrupt the ionic bonds held together by the crystalline structure. So some ionic bonds are stronger than others. So some ionic compounds are water soluble if if the attraction to water molecules is greater than the attraction of the ions, it's going to be soluble in water. That means it will dissolve. But if the attractions between ions are stronger than the attractions to water molecules, then those are water insoluble. Okay. So let's look at an example of two different things. So we have sodium chloride, and this is a bad picture of a beaker. And we put that into water. Those ions are going to separate. Okay. And this is called drawing your principal species in solution. I'm just stating what's there. But if I put barium sulfate into this beaker, the ions are not going to separate. So this is soluble, and this is insoluble. Okay. Now, the other solvent we're talking about is hexane, which is just a chain of carbons and hydrogens. So it is nonpolar. So it's a nonpolar molecule with no ability to disrupt an ionic bond. Um, so all ionic compounds are insoluble in hexane. Okay. So another property is electrical conductivity. So if it's a water-soluble ionic compound, water-soluble ionic compounds will conduct electricity. And this is due to the movement of the ions in solution. Let's see, with the sodium chloride, we have these charged particles floating around, and those are going to conduct electricity. Whereas with the barium sulfate, um, there are no charges because they are still stuck together. So it will not conduct electricity. So the third characteristic we are looking at is a melting point. So since ionic bonds are strong and the entire crystalline structure is held together by ionic bonds, the melting points of these ionic compounds tends to be high. It takes a lot of energy to break an ionic bond. So let's compare that to some molecular compounds, also called covalent compounds. And so, since a covalent compound's crystalline structure is held together by intermolecular forces, which are much weaker than bonds, they have very different physical properties, physical and chemical properties from ionic compounds. So let's look at those. So let's compare water and hexane solubility. So it depends on what type of covalent compound you have. So polar covalent compounds will dissolve in polar covalent solvents. So for example, sugar is a polar covalent compound. So it will dissolve in water. So we would call them water soluble. Okay, and nonpolar covalent compounds. Those will dissolve, you guessed it, in nonpolar covalent solvents, such as hexane. So they are not water soluble. They are hexane soluble. Okay, so for electrical conductivity, we have no charges. Um, so they do not conduct electricity. Charges are required. And so our final characteristic is the melting point. So with the weak intermolecular forces, holding the crystalline structure together, that causes the melting point to be low. Okay, so let's make a table to summarize this. So the crystalline structure of a covalent compound is held together by intermolecular forces, which are weak, and ionic compounds are held together with ionic bonds, which are strong. For solubility, ion or covalent compounds will have the two types: the polar compounds in water, are soluble in water, and nonpolar are soluble in hexane. Okay. And so for ionic compounds, some will be in water. If they're going to be soluble in anything, it will be in water, and none of them in hexane. Okay. So conductivity, we have no real charges, no full charges, so no. But we do have charges, so if soluble. So yes, if water soluble. Okay. And finally, the melting point for covalent compounds will be low due to the intermolecular forces. And for ionic compounds, it will be high due to the ionic bonds. That concludes our lecture for experiment 32E. I look forward to seeing you in lab. Thank you for your attention.